Welcome to the second class. Just to recap, last class we did discuss about how the working of the CMOS and the PMOS transistors. We also saw what we mean by fully restored logic. We also constructed two logic gates, namely the NAND gate and the NOT gate, using these two transistors, namely PMOS and NMOS. We explained why these transistors take very less power, why circuits constructed using these transistors take less power. So, to some extent we gave you an idea about how to build circuits using PMOS and NMOS transistors. In this class we will go to a little higher level of abstraction. We will cover what we mean by a functionally complete set of gates. A functionally complete set of gates is a set of gates using which we can realize any logic function that is given to us. So let me just explain this concept in a bigger detail, and why I am going to do this is to also teach the CS students who are attending the course some basic notions of how to define, how to arrive at a definition for some concept. This is very important. This language is very important for people to express certain theory or certain concepts in a very formal way. So any logical function, any Boolean function can be expressed either in terms of sum of products or product of sums. Once I have a sum of product or product of sum representation, is the audio clear? VPCOE, is the audio clear? Right. So the moment we have a sum of product or product of sum representation, then we can realize the circuit using the gates, namely AND, OR and NOT. So let us take a simple two input function . So this can be realized as, let this symbol stand for NOT, this symbol stand for OR, and this symbol stand for AND. So this can be realized as not P and Q or P and not Q. So essentially I can realize this function using just the AND, OR and NOT gate. This proves that any Boolean function given to you can be realized using the 3 gates, namely AND, OR and NOT. So AND, OR and NOT, this set is called a functionally complete set. Now let us go to the next step. I hope in your digital logic course you would have attended, you would have learnt about the De Morgan's law. Let me quickly revise this. The De Morgan's law gives a relation between AND and OR. Basically it gives you a methodology by which I could realize an OR function using and an AND function using OR. De Morgan's law, one part of the De Morgan's law is not of P or Q is equivalent to not P and not Q. This essentially means P or Q is equivalent to not of not P and not Q. This essentially states that the OR function can be realized in terms of not and AND. So that means, let us take this set. In this set, the OR function can be realized in terms of AND and NOT. By this we can infer that using AND and NOT alone, we can realize any function that is given to us. The OR is not necessary, because the OR, if I get an OR, I know how to realize this OR function in terms of NOT and AND. So AND NOT also becomes a functionally complete set. Similarly, the other part of the De Morgan's law states that not of P and Q is equivalent to not P or not Q. In other words, P and Q is equivalent to not of not P or not Q. By this we understand that the AND function can be realized using just NOT and OR. So if I take this set AND or NOT, the AND function can be realized using OR and NOT. So by this we infer that OR NOT is also a functionally complete set. So to sum up, AND OR NOT is functionally complete, AND NOT is functionally complete, or not is also functionally complete. So we are seeing three functionally complete set of gates. Using any of these set, using the gates in any one of these sets, we can realize any Boolean function that is given to us. Now let us take this functionality, namely NAND. I will represent the symbol NAND by this. Now please note that P NAND Q is equivalent to not of P and Q. P NAND P is equivalent to not of P. Using these two, we can realize that not of P NAND Q is equivalent to P and Q, and this is equivalent to P NAND Q NAND P NAND Q is equivalent to P and Q. So by this we see that both the NOT function and the AND function can be realized in terms of NAND alone. Both the AND function and also the NOT function can be realized in terms of NAND alone. As you see here, the NOT function can be realized in terms of NAND. The AND function can also be realized in terms of NAND. From this, what we can say, since AND and NOT form a complete set, functionally complete set, and the AND function could be realized in terms of NAND, NOT also could be realized in terms of NAND, we can go ahead and say that NAND gate is also functionally complete. Similarly, let us look at another function which is NOR. I represent it by the symbol, by this symbol, a down arrow. P NOR Q is equivalent to NOT of P or Q. P NOR P is equivalent to NOT of P. So NOT of P NOR Q is equivalent to P or Q. So P NOR Q NOR P NOR Q is equivalent to P or Q. So looking at this carefully, both the NOT gate and the OR gate, or the NOT functionality and the OR functionality, can be realized in terms of NOR. So since OR comma NOT is functionally complete, and that the OR functionality and the NOT functionality can be realized in terms of NOR, this NOR gate also becomes functionally complete. So to sum up this discussion, given any Boolean function, since we can have a sum of product or a product of some representation, that Boolean function can be realized in terms of AND or NOT. and since the OR by De Morgan's law, the OR functionality could be realized in terms of and not, and not. Any Boolean function can also be realized using just and not gate. Similarly, any Boolean function can be represented using only OR and NOT gate. Now since and not both functions could be realized in terms of NAND gate, any Boolean function can be represented using only or realized using only NAND gate. Similarly, any Boolean function can also be realized only using NOR gate, because OR and NOT could be realized using the NOR gate. So all these 5 sets, we are seeing 5 sets here: set number 1, set number 2, set number 3, set number 4 and set number 5. All these 5 sets are functionally complete set. Functionally complete set of gates. Let me number it as S1, S2, S3, S4, S5. All S1 to S5 are functionally complete. In this, S2 to S5 are minimally functionally or minimal functionally complete. Why are they called minimal? Please understand it is AL, minimal, because if you remove any gate from this, then the set ceases to have that property. For example, if I remove NOT from this gate, then this ceases to be a functionally complete set of gates, because using just AND gate I can't realize every Boolean function. Similarly, if I remove a AND gate and I have only NOT, still it ceases to be a functionally complete set. Similarly, in the case of OR and NOT, both these gates are absolutely necessary for you to realize the Boolean function. Similarly, in the case of NAND, NOR. So these 4 gates, 4 sets are called minimal functionally complete set. Please note, again note the word minimal. While in the case of S1, it is not minimal, because if I take, it is not minimal because if I take out and pull out and, still using OR and NOT I could realize any Boolean function. So if I remove one gate from S1, I can remove one of the gates from S1 and still maintain the property of functionally complete set of gates. So S1 is not minimal functionally complete set, while S2 to S5 are minimal functionally complete set of gates. Out of these 4 sets, S4 to S5, S4 and S5 are minimum functionally complete set of gates. Please again note this here, minimum. Of all the minimal functionally complete set, the sets with minimum cardinality, the least set with least cardinality, they are called minimum functionally complete set of gates. So out of these 4 sets, this has cardinality 2 because it has 2 elements, this has cardinality 2, this has cardinality 1 and this has cardinality 1. Out of the 4 minimal functionally complete set of gates, I have 2 of them which has the least cardinality, namely S4 and S5, and they are called minimum functionally complete set of gates, right. So any decent paper, research paper that you try and study in computer science will mostly have these 2 terms, minimal, minimum, maximal, maximum. You should understand the difference. There is a huge difference between minimal set or minimal property and minimum set or minimum property. Between those L and the M, it makes a heaven to a hell difference. Okay, so I am just basically using this concept of functionally complete set to explain you the difference between minimal and minimum. Okay, so this completes our discussion. So that is why if you go and look at any fabrication unit, what they will realize is a NAND gate. They would have a circuit made for NAND gate. They have circuits made using just NAND gates, and using that circuit, which you call circuit, we can realize any larger circuit, right? So that's why fabrication units mostly concentrate on implementing, say, the NAND gate or the NOR gate, because using that we can realize any other circuit. Okay, so if there are any doubts, you can raise hands at the end of the lecture around 8:35, another 15 minutes down the line. You can raise any doubts and I will answer. I am reserving 15 minutes for doubts. So 8:35 we can start the question answer session. So in digital hardware there are two types of circuits. One is the combinational circuits, another is the sequential circuits. Combinational circuits, they are called combinational because their output actually depends upon the current set of inputs, right? If you take a AND gate, the output of this AND gate depends upon the current value of the inputs, namely A and B. So this is an example. So the output actually depends upon the combination of the inputs, a combination of the values assigned to the inputs, and that is why these circuits are called combinational circuits. The other type of circuit is called a sequential circuit. A sequential circuit, the output of a sequential circuit depends upon the current inputs given to the sequential circuit and the state of the circuit, that is some values that depend upon the previous set of inputs. So the current output not only depends upon the combination of the current inputs, but also depends upon some values that in the circuit that are basically set because of the previous inputs that were given to the circuit. So essentially the output of a sequential circuit depends upon the history of the inputs that are being assigned to that circuit. So now this should have been detailed. I hope it has been clear, taught to you in the digital circuits course, but just I will give you a small introduction into the representation of a sequential circuit. A sequential circuit basically has a combinational circuit to which some inputs are given and some outputs are collected, and some outputs of these combinational circuit are stored in registers, and the output of that register is also given as input to the combinational circuit, and the register is also governed by a clock. So you apply an input, that input is processed by this combinational circuit and some output is generated. In addition, some part of the input is also saved in a register, and that values are again fed as additional inputs to this combination circuit. So if you take the output is a function of the current inputs plus the contents of this resistor. So this is where the history of the circuit, history of the inputs or the state of the circuit is being stored. So the resistors, the value of the resistors represent the state, the current state of the circuit. So the output of a sequential circuit is a function of its input, the current inputs and the state of the circuit. And the state is updated at every clock pulse. So when the new clock pulse come, the current state is stored and that is given as input for the next clock cycle. So this is how a sequential circuit works. Some simple sequential circuits that we see are the counters and registers. Basic building blocks for these counters and registers are the flip-flops or latches. So all these concepts you would have learnt in your digital circuits course. Just to wind up this particular discussion, this particular representation is a generic representation of a sequential circuit, and these are examples of a sequential circuit. Now let us go ahead and see how these combinational circuits and sequential circuits be used to build certain components in the computer. Some interesting arithmetic circuits which you would have again covered in your digital circuits course are the adders, multipliers, dividers, comparators. The adders add numbers, multipliers multiply, divides, comparators compare two numbers. So these are basic arithmetic circuits. In addition, you would have seen certain circuits like the multiplexers, and decoders. All these are combinational circuits. So what will the multiplexer do? Let me just basically give you the example of a 2-to-1 multiplexer. A 2-to-1 multiplexer brightness is not, make it is very dull. Yeah. So let me explain you what a 2-to-1 multiplexer does. The 2-to-1 multiplexer has one select input, one output and two inputs, namely A and B. This is called the 0 input and this is called the 1 input. If select is 1, then output would be B. else output will be A. This is the functionality of a 2 to 1 mux. If select bit is 1, then the output will be B. If the select bit is 0, then the output will be A. Right. Using this multiplexer, let us now construct a small ALU. And ALU stands for Arithmetic Logic Unit. Let me say that the ALU that we have has an adder, a multiplier, a divider, and a comparator. Now let us number these units as unit number 0, unit number 1, unit number 2, unit number 3. In binary, this is unit number 00, this is unit number 01, this is unit number 10, this is unit number 11. Now I am adding or multiplying or comparing or dividing two numbers. I am performing one of these operations. So let me say those two numbers are stored in register 1 and register 2. They are ALU register 1 and register 2. Now these numbers are fed into all these units. These numbers are fed into all these units. Now these all these units will generate an answer. So suppose they are comparing, say the ALU is comparing either two 8-bit numbers or adding two 8-bit numbers or multiplying two 8-bit numbers or dividing an 8-bit number by another 8-bit number. So the worst case multiplication will give me an answer which should be 16 bits in length, while adder will give me an answer which is say 9 bits in length. Comparator will give me only 3 bits, whether it is equal to, less than, or not, and division can give me some number which can also be within 8 bits. So let us say I want to collect these outputs in one register, whatever be it, and that register would be the ALU output register. There will be one register R out on which I have to collect this. So, which one will I collect? That depends upon the operation. So, what we do here is that let me take one bit of the comparator. So, I put what we call as a 4-to-1 mux. I put a 4-to-1 mux onto which one line each of these units are fed in, and I have a two select signals, select 0 and select 1, and this output is connected to one bit of R out. Like that, let me assume that there are going to be 16 outputs from each of these units. I will have 16 4-to-1 mux I will have 16 4-to-1 mux, and for each of these mux the same select input would be given, namely S0 S1, S0 S1, S0 S1, and to each one of them one of these lines would be connected. So, the 0th line of the each is connected to this, the first line of each one of this would be connected to this, the second line to this, and so on till the from 0 to 15th line, and each one of this output will go to the 0th line of this register, the 0th flip flop of this register, the first flip flop, the second flip flop, and it will be the 15th. Right. So, I have, if the answer is maximum 16 bits, I am going to have 16 4-to-1 multiplexers, to which one output line of each of this unit will go to each one of these multiplexers, and I use the select bit, namely S0 and S1. And so, if I want to do an addition, I just set this as 0 1, and what will come out is the output of the adder. So, I will have 16 lines in which the first 7 lines are relevant to me. I will take those first 7 lines out and I will get an answer. Similarly, in the case of a multiplier, if I want to do multiplication, I put 1 0 as the select, and the answer I will get would be the multiplied value of R1 and R2. So, that 16 bit I will collect. In the case of division, again I will get some some quotient and some remainder which I can collect. In the case of comparison, I will get a 16 bit answer in which the first 3 bits are relevant. The first bit will say whether it is equal to, second bit will say whether it is less than, third will say it is greater than. So, depending on what operation I want, I can adjust this select bit and collect the necessary answer from any one of these 4 arithmetic units, and that is how a simple ALU can be constructed. So, the ALU comprises these arithmetic circuits along with a multiplexer which selects out of several operations which operation, the result of which operation is needed, and that result it collects out in another output register which can be used for further processing. So as you see, this ALU has some sequential circuits, namely in the form of registers. This has lot of combinational circuits, some in the form of arithmetic, some needed for doing the arithmetic, and some needed for doing the selection. That selection in some way we can call it as the control. Some combinational circuit is used for processing the data, some combinational circuit are needed for establishing the control. So even in this small ALU, there is a combinational part, there is a sequential part which is essentially used for storage. There are combinational parts which are used for performing the arithmetic operation, namely comparator, adder, multiplier and divider, and there are combinational parts which are used for controlling the operation, namely these multiplexers. So in essence, if you take a digital circuit, if you take a digital computer, this comprises the hardware inside comprises sequential and combinational circuit. Typically the sequential circuits are used for storage and of state, and the combinational circuits are used for two things: one for performing the arithmetic logic operation or processing the data, and the second thing is for controlling the flow of data. In some essence, these multiplexers control the flow of data, basically saying if it is an addition operation, the adder output alone goes to the out and these are stopped, while if it is a multiplication, the multiplier's output alone goes to the register while the others are stopped. In some essence, this establishes a control. So we will discuss about this in greater detail during lectures 5 and 6, where we will talk about the control logic and the data logic. But as far as the discussion on digital circuits is concerned, we basically want to build a small component and show you how the combinational and sequential circuits are connected together to realize some functionality. Now I open up for questions. We have 10 minutes and I request all of you to raise your hands so that I will answer the question. Yes, PCAP.
So which logic gate the multiplexer can act as
Yeah.
alternative? For which logic gates the multiplexer can act as an alternative?
Can you talk loudly, and your audio is not proper here. Please talk loudly. Which logic gates?
For which logic gates the multiplexer can act as an alternative?
Which logic gates the multiplexer? I am not able to clearly hear your question. Please keep the mic close to your mouth. Which logic gate can act as an alternative to multiplexer?
For which logic gates? Sir.
No, I am not getting the question. Please type it in the chat. Yes.
Good morning. Sir, in functional
Hello?
complete set of gates. Sir, in functional complete set of gates, why
Yes.
S1 is class of minimal functionally complete set.
What is it? Functionally complete gates? I am not able to hear you properly.
So null set S1 is not a minimal functionally complete set.
I am not able to hear. Can you please type on the chat? Please type on the chat. Which logic gate can act as a multiplexer? A multiplexer is typically realized using an AND gate, OR gate and inverter. Let A be the 0 input and B be the 1 input. So the input, if the select bit is 0, irrespective of B, A is out, and when select bit is 1, irrespective of A, B is out. Okay, so the circuit can be realized as when your select is 0, this would be A and this will be 0, so the answer is A. When the select is 1, this is going to be 0, while this is 1, this is B and this is 0, your answer is B. So when select is 1, the answer is B, when select is A, the answer is 0. So this is how you realize a multiplexer functionality. So you can design specific gates to actually realize this functionality. So you can basically realize a complete CMOS PMOS implementation. You can create a gate which can basically create this functionality also. So this is the function that is needed. So how do we realize that? There are many ways by which you can realize it. So you can basically draw a Karnaugh map and get a gate which can do this. Yes? Yes. Your volume please. Volume please. QEECTN, I can't hear you. Volume. The JSE question was why set S1 was not a minimally functionally complete set. why this set is not minimally functionally complete. That is the question. This set is not minimally functionally complete because the definition of minimal functionally complete set is that I should not be in a position to remove a gate and still maintain the property. In this case of AND or NOT, I can remove of AND, I can just retain OR and NOT and still say it is functionally complete. Similarly, I can remove OR and I can just retain AND and NOT and still say it is functionally complete. So this particular set is not called, is not a minimally functionally complete set. It becomes minimal only if I can't remove any gate. If I remove that gate, then that property is gone. For example, if I take AND NOT, this is minimal functionally complete because if I remove a AND gate, then I can't realize any function. If I remove NOT gate, then I also cannot realize any function. So by removing a gate in this set, I lose the property that this is still functionally complete. So that is why AND NOT is called minimal functionally complete set. But in the case of AND or NOT, that is not valid. If I remove AND, just using OR NOT, I can realize all functions. If I remove OR, still using AND NOT, I can realize function. So that means there are some elements which can still be removed and still I can maintain the property of functionally complete set, and that is the reason why S1 is not minimal functionally complete set.
What kind of logic
Yes.
gates are used for implementing comparators?
What
kind of logic gates?
see all the logic gates finally are realized using NAND gates or NOR gates in practice. So for example, a XOR gate for implementing a comparator, but ultimately when you see how XOR gates are implemented in the real hardware, it is again using NAND gates. So all logic functionalities, if you really see how it is implemented on a chip, they will be using the NAND functionality. Fine?
Thank you, sir.
Yes.
What is the difference between latches and flip-flop?
What is the difference between latches and flip-flop? This is actually something that should have been taught in your digital logic course, but anyway I will tell you. A latch is a level sensitive a latch is a level sensitive storage element. A flip-flop is a edge triggered storage element. A latch is a level sensitive storage element, flip-flop is a edge triggered storage element. So let me say this is a latch and this is input of the latch, this is output of the latch, and this is clock given to the latch. Similarly, let me say this is a flip-flop, this is the input given to the flip-flop, output of the flip-flop, and this is the clock. Now let me draw the clock. and let me draw this is the clock, and let me draw the inputs. Now what will happen in the case of a latch? Say let me call this OL and OFF. OL will behave like this. Whenever the clock is at 1, whenever the clock is at 1, the input will go to the output. Whenever the clock is 1 in the case of the latch, the output will become equal to input. So for example, in this case, let us assume without loss of generality it was 0 till this point. When the clock became 1 here, please note, the output of this latch will follow the input. So this will go like this, and still here it is 0. Now at this stage, there is some transition here in the input, but that will not come here because the clock is 0 here. In this part, whatever happens to the input, that will not go to the output. So this will remain like this. And again at this part, this will go and this will stay, and again this will come down. So this is how a latch will behave. In the case of the latch, when the clock is 1, whatever is there on the input will go to the output. When the clock is 0, whatever was lost there on the output when the clock was 1, that will be retained. So the latch is still a storage element, but it will retain whatever was there on the latch when the clock was lost at the level 1. So let me explain this input again for you, the behavior of this input. Assume initially the input was 0 in the previous clock. When the clock became 1 here, this output became equal to input, and as long as the clock remained at 1, this output is following exactly the input. So it is following till this part. The moment clock became 0, the output remains at what it was when the clock was 1 last. So it is at 0, it continues to be remaining at 0. So in this intermediate period, when the clock is 0, when the output changes, those changes are not reflected in the output of the latch. Now this goes on again when here the clock goes high till this part, between this part and this part, the latch behaves exactly like the input. So the input goes high in the middle of this goes high, then again it is high here. Now the clock comes down. Please note that even though this input becomes low at this point, as per the definition of the latch, the last stored value is still retained. So what was the last stored value? It was 1 when the clock became 0, and so that 1 will continue till the next clock pulse. Once the next positive edge comes, again this becomes 0, so this continues to be 0 and so on. So the output of a latch is equal to the input when the clock is 1. The output of the latch is the last assigned value of the input when the clock was 1, once the clock becomes 0. So when the clock becomes 0, for example here, the value of the output for this entire duration when the clock is 0 is the value of the input at the last point of time when the clock was 1. For example, the clock was in this duration, the clock was 1 here, and that value was 1. When the clock was here, that value was 1 on the input. So the output retains that value 1 till the clock becomes 1 next. As long as the clock is 0, the output, the latch retains the value of the last assigned value of the input. So in this way, the latch actually depends upon the level of the input, level of the clock, to decide whether the output should be equal to input or the old value of output should be retained. But in the case of a flip-flop, let me just draw the OF. In the case output of a flip-flop, it depends upon what was the value at the when the clock was going from 0 to 1. We called it as an edge triggered. So what was the value of the input when the clock went from 0 to 1, and that is basically used for determining the value of the flip-flop. For example, let us again assume this is 0. When the clock goes from 0 to 1, the input became 1. Input was 1. So this retains at 1 and this goes. So till the next edge, whatever happens to the input, it is not seen on the output. The flip-flop retains the value of what was the value of the input in the when the clock goes from 0 to 1. And now when it comes to the next cycle, at this point the input became 0, so the output also becomes 0. Now at this point the input still retains at 0, the output is at 0. At this point the input is 0, this is 0. At this point still the input is 0. So this is how the flip-flop behaves. Is it clear?
Thank you, sir.
Yes. Huh?
Hello. Good morning, sir.
Yeah, JSE. Yes, please tell the question.
Now, what will be the number of inputs and outputs for comparator, adder, multiplier, and divider?
What are the number of inputs for see, number of inputs, for example, if I am comparing two 8-bit numbers, in a comparator the total number of inputs would be 2n bits and the output will be 3 bits. One for saying whether A is less than B, A is greater than B, A equal to B. Okay?
But here in the diagram, draw only one output.
Okay.
From adder, as well as from multiplier, as well as divider.
No, I told you there will be 32 outputs. I told you there can be up to 16 outputs, but whatever is relevant we can take. 3 bits are thing, the remaining things would be don't care.
So if you multiply two 3-bit number,
You get 2 into k bits.
So if we multiply to 8-bit numbers, we will get 16. We will get output as a 16-bit number. Within our register, our out we can show only 4-bit numbers. I think we have only 4.
You get 2 8-bit numbers. Hello?
Sir?
Hello? Yes. If you multiply 2 8-bit numbers, you get 16 bits.
Yes, sir. But how to store that 16-bit in the register R out? You can see there are only 4.
So the register, that's what I said, the register can be that maximum number of bits. So the multiplier gives you the maximum number of bits, which is 16. So I will store all the 16 bits because I have 16 4 to 1 mux. 16 bits from the multiplier will come and be in the mux. Through the mux will come and stay in the register. While for the comparator, I am only interested in 3 bits. So only the first 3 mux, these inputs will come. The remaining 16 minus 13 mux, it will be left as don't care. Okay? Right. So I am ending up the class. So any questions to ask in the chat.